In this video, we want to take a look at inference in regression lines. And we want to start with our conditions that we'll need to check and how to check them before we can do a confidence interval or a hypothesis test. So there are actually a lot more conditions than what we're used to in our other tests. And you can remember these conditions with the word linear, L-I-N-E-R, to remember the 5 conditions that you'll need to check. The first condition that you'll need to check is that the actual relationship is linear. The second thing you'll need to do is you'll need to check for independence, which means you're drawing the sample with replacement. Remember, if it's not truly independent, it's good enough if your sample size is less than 10% of the population. We also want to make sure that our x values and y values have a normal distribution. For any given x, we want the y values to have a normal distribution. We also want to check that the standard deviation in our y values are equal for every single possible value of x. And we want to make sure that we've either done a random sample if we're doing a study or observational, and we want to make sure it's randomized if it's an experiment with random assignment. So here's how we go about checking these conditions. To check whether or not your data is linear, we want to do a scatter plot and look for that linear pattern. We also want to look at the residual plot and make sure that it's a random scatter with no patterns. And we would like our values for our residuals near the center to be close to 0. To show that something's independent, and we just want to look at our sample size and make sure that it makes sense that our sample size would be less than 10% of the population. To tell if our sample is normal, we will use some sort of data display like a stem plot, dot plot, histogram, normal probability plot. And we're looking at those to make sure they are symmetric. To check to see that the standard deviation of the residuals is approximately equal, you want to look at the residual plot and look at the line where the residual is 0. And you want to look at how far above or below your residuals are from that line. And as you read that graph from left to right, from the smallest to the largest x value, you're hoping that those stay roughly the same. As in many of our prior examples with intervals, confidence intervals, they will often just say in the problem that there was a random sample or that there was random assignment. That is often the case here as well. So now we're ready to finally look at an actual confidence interval. We have the same general formula that we've been using all semester, where we're doing the statistic plus or minus the critical value times the standard deviation of the statistic. In this case, our statistic is our slope. We're going to use a t-distribution, and we're going to have our standard error rather than the standard deviation. And since we don't know the population standard deviation, since we're estimating it with the standard error of the sample, we're going to be using t rather than z for our critical values. Now we'll be using computer output, so you won't need to be able to calculate those standard errors with the formula shown here, but you do need to know the degrees of freedom when you're doing a line of best fit or least squared regression line is n-2 rather than n-1. The reason here is because we're estimating the extra part where we're estimating the standard deviation as well. So since we have a second estimation, we're doing n-2 for our degrees of freedom. Similarly, we'll use that general to specific model for our test statistic as well, where we start with our null hypothesis being that we're accepting whatever we're being told is the true slope, and then our alternate being that we think it might be greater than, less than, or not equal to that. And then we're doing our our test statistic minus the parameter divided by the standard deviation of our test statistic to get our t-value, where we'll go to our table to find that number to put in for our critical t. Similar to what we did in the beginning of the year, where if our alternate hypothesis had a greater than sign, then we were looking for the tail on the right of our distribution, or if our alternate hypothesis had a less than sign, we were looking for the part of the tail that would be shaded on the left, or if it was not equal to, there would be two tails. That all holds true here as well. Let's look at an example to go through our four-step process, our state, plan, do, conclude, for our confidence interval. So here we have a regression line related to the miles that are on a vehicle and its worth. And we see that it has this negative slope. We also see here is our residuals, and we then also see a histogram of the residuals. And we have our computer output as well. And we'll use all of this to come up with a 90% confidence interval for the slope. For the state part of our four-step process, we're going to give our parameter, our statistic, and our confidence level. So our parameter is the true slope of the population for our least squared regression line in the price of the truck versus the miles driven. Our statistic comes from our computer output. That's our sample slope. And then they gave us that we were doing, or we wanted to do, a 90% confidence interval. So that's our confidence level. For the plan part of our four-step process, we should name the test. We're going to do a one sample t interval for beta sub 1, and we should check our conditions. Remember the acronym linear. So first we want to, for L, show that our scatter plot shows a linear pattern, which it does, and we want to see that there's no pattern in the residual scatter plot, which is true. So we meet that condition. The I stands for independent, and although we were drawing these without replacement, it's reasonable to believe that 16 F-150s is less than 10% of all used F-150s, so we'll consider that one met as well. N, we want the residuals to be normal, so we look at the histogram here of the residuals, and we don't see a strong skew or any outliers, so we'll assume that normal distribution of the residuals is met. E, we want the standard deviation of the residuals to be equal, and that means when we look at the data points above and below on our residual plot, we want them to have that same vertical spread, which this looks like it meets. And then last, we want to make sure that it was a random sample, and that was stated in our problem. So this does meet the conditions. Next up is our do part of our four-step process. We start with our general formula, where we do our point estimate plus or minus our margin of error. And then we move on to our specific formula. And our B sub 1 is coming from the table of computer output. Our critical T comes from our confidence level of 90%. We had a sample size of 16, so our degrees of freedom is 16 minus 2 or 14. And using our calculator, that's where we get the 1.761. And our standard error of the slope is also coming from our computer output. And then that simplifies to an interval for our slope being somewhere between negative 0.21744 and negative 0.10840. And finally, that takes us to our conclude step. This should look familiar from our previous confidence interval interpretations, where we have that same fill-in-the-blank format. So we'll say something like, we're 90% confident, where that is your confidence level, that the interval from negative 0.21744 to negative 0.10840, and those are the endpoints of your confidence interval. We're 90% confident that the interval from negative 0.21744 to negative 0.10840 captures the true slope of the population least squared regression line, and then you give the context. In this case, we were coming up with a line relating the prices of the used truck to the miles on that used truck.